Okay, so welcome to Unit 3, which is all about sampling design and experimental design. Really, it's all about where data come from. Data being, for statistics' sake, values, numbers, responses, basically, that we want to use to tell us about a more general or broader scenario. So to start this out, we're on notes 3-1. We'll break this into 3 sections. This is a smaller section that's starting us out to understand randomness and why it's so important. Section 2 and 3 will be about sampling design and experimental design, the 2 basic places where we get data. So we're going to start with talking about randomness and simulations. So to give you a feeling for this, why are we doing this? We're going to be talking a lot about populations and a lot about samples. When we think about samples as a sample basically are the data that come from our observations or our collection process. But they're only part of the picture. We really want to know about the population, the whole process, the whole population, or what's going on in the long run. So the thing is, how do we understand when we're seeing a good sample or a bad sample? More importantly, how do we make sure we go collect a good sample that's going to be reflective of the population? Well, it has to do with randomness, really. We basically will need to see a random collection from a population. So let's talk about that. I'm going to define random by first talking about bias. Now, why do we have to do all this? Why is there going to be all this math involved, all these higher level ideas? Really one simple reason. Humans can't be truly random. I'd like to give you a demonstration now. I'm going to give you 4 numbers. I do this in a big class format. It's more telling, but you're just one watcher. You'll still understand the process. I'm going to show you 4 numbers, just 4 digits actually. I'd like you to randomly, without bias, without any particular purpose, just to choose one. But choose one and commit to it. Choose one right away. You ready? Here it comes. If you would, please pick one of these 4 numbers. You already have it. So anyway, if I had many people do this, I should find, if everybody's doing this randomly, about 1/4 of them will pick 1, 1/4 will pick 2, 1/4 will pick 3, and 1/4 will pick 4. We'd look at the distribution in the long run as being a uniform distribution, where every choice has an equal probability of occurring. What we tend to find when doing this, what I found years after years of doing this, is people really prefer the 3. Even when told there's no point to this, there's no matter, just to pick something random, they tend to pick 3. Second most popular is 2. Third most popular is 4. And very few people, but sometimes pick a 1. So it looks like that. The thing is, even when people want to be random, don't want to have bias, it's not really possible. We're all born with our biases, our favors, our preferences, so we need something else. So this is all going to be about how do we generate random data, and how do we simulate a long process of generating random data. So what is random? To be random means to not have bias. So let's go to the bias. So we're going to use the word bias a lot. Careful, in lay speak, people use bias a lot, and it's often not used correctly. Bias doesn't mean necessarily error or a mistake. A bias is more a systematic mistake. It's a systematic favoring of certain outcomes. For instance, I just showed you some a biased process. People are more likely to pick a 3. It's a biased process. Another way to think of bias is such that we can kind of predict what's more likely to happen. We can make a prediction about what's going to happen before we actually go out and collect data. That's where we get this bias thing from. So get something that's truly random means without bias. More about that in a second. I already talked about the whole point of this being, really we want good samples, to be random samples to tell us about a population. So what is this? The population will define the whole course as being the entire group of individuals you want information about. That could be a huge population. We're used to using that word as in the population of, United States citizens, things like that. But the population is just the entire group you want to know about. It might just be how the class did on the next AP unit exam. It's that class, right? Maybe there are only 30 in that population. What the sample is, though, the sample is a subset of the population. It's a part of the population that we actually examine. We only see this in order to gather information about the population. Purpose being is when we can't have the whole population, we only have a sample, what will that tell us? We're going to talk about a lot of sampling, sample types and methods in this chapter, but I want to introduce one right away, which is a pretty tricky one for some people to get, but it's a really like the most random sample you could have. And it's one that's important to bring up because I'm going to use it a lot. It's called a simple random sample, an SRS. As we'll find out, random samples are just when we have a random collection from the group. That can be a lot of different ways, a lot of different things. But this selection method ensures that every possible sample has an equal chance of being the sample ultimately selected. Notice it does not say the selection method ensures every possible individual or person or thing has an equal chance. Actually, any random sample should basically have everything has an equal chance, or maybe not. This is that every possible combination has an equal chance. Let me show you what I mean. Let's say I have my class and I have some girls, some boys, and I want a random sample from that population of just 2 students. I decided to do it this way. I put all the boys' names in a hat, put all the girls' names in a different hat, shuffle up the boys' names, grab the card, shuffle up the girls' names, grab the card, those 2 students come forward. That's a random sample. That's considered a random sample of 2 students from that population. That is not a simple random sample, the 1 boy, 1 girl. Why? Not every possible combo had an equal chance of occurring. Example, it was impossible for me to get 2 boys. Since that sample had a 0% chance of occurring, we can't say every sample had an equal chance of occurring, so it doesn't really work. Lastly, we're going to talk a lot about simulations. Simulation is not actually going out and getting the sample or samples, which can be time-consuming, especially if you want many samples. It's basically like sampling done for pretend at home with a process. It's an imitation of the chance behavior based on the model, basically whatever the population looks like, but that accurately reflects the experiment under consideration. So we're going to talk about doing that. So if humans can't generate random data, how should we generate random data? First off, a couple of things that you've probably used in your past and can still continue to use. A coin, or coins, right? Sure, coin or coins. Now, that really only works if you want to have 1 coin and you have 2 choices that should be equally probable. Heads, tails, that works just fine. Multiple coins gets different probabilities, but that's not wildly useful, but it can be useful sometimes. Another one we use a lot are a die or dice. If you have 1 die, that can be very useful as long as you can break up the different events into probabilities out of 6. That could still work for half and half, right? 1, 2, 3 versus 4, 5, 6. 1 and 2 versus 4, 5, 3, 4. 1 and 2 versus 3, 4, 5, 6. Excuse me. So it'll be 1/3 versus 2/3, but it's not wildly useful. That's not all the things we have. A really easy way we can do it, we have an idea we call names in a hat method. If you think about that literally, we're saying what I say about the boys and girls thing. I put all the people's names or things enumerated in a hat, shuffle them up, and pick them out one at a time without replacement. In reality, there's no hats when we talk about this idea. We don't actually usually use cards. I'm thinking more about the idea how we do the lottery, and we have the balls spinning and they shoot up one at a time. That's the idea of names in a hat. But that can work. That is a way of generating an SRS. Any sample of those balls, for instance, could be equally likely as any other possible sample. Now, we're not going to be often throwing names in hats or having a big urn full of balls that spin, although it'd be fun. What we're going to be able to use is a random digit or number generator. We can tell a system, a calculator, program, computer, what we'd like to see, give them the weights, and let it do it for us. Now, the nice way we can do this, we can actually do this in our TI calculator. How does this look? Let's take a look real quickly and see how this goes. I'll try to put this up here. It might not be that easy to see, but I'll go slow and talk it out loud. I suggest you do take out your TI calculator or pause it, and then try this along with me. All right, so it's flashing. Hopefully you can see it, but I'll go through this button presses with you. Anyway, we start with hitting the math button, arrow over to probability, PRB, arrow down to, there's a bunch, but here's one that's very useful. We'll find randint, random integer, that means. Your screen might not look at mine, depending on what version that you have, but anyway, you can put the lowest number you'd want, maybe 1, comma, the highest number you want. Maybe I have a class of 25 students, comma, I can close it up, and every time I hit it, it'll give me another random value from there. Now, this is doing it with repeat, so I might get the same person twice. I can either ignore that or count it depending on what I want. So you got 2 12s, for instance. One last thing I'll show you that can be useful. Math, probability, random integer, no repeats. Sometimes it's nice to have a whole group, but in a randomized order, so we can use that. What I would do here is I'd say 1, comma, maybe 25, close it up, and just hit enter, and it'll give me all the values in a random order. This would be great if I want to break things up, or imagine if phys ed teachers and people at the playground use this to devise teams. You number everybody, you're on this team, you're on that team, you're on this team, you're on that team. Anyway, it's a good way to do that, and it does go through, if you arrow to the right, all the values, 1 through 25. So those are acceptable ways to do that. We call that using a random number generator or random digit generator. Now, the one thing I'm going to train you how to do next is to use a random digit table. This is used without technology, and we'd end up going and using a random digit table that looks like this. I'm going to pause this now, and we'll start the next section following this, so these aren't too long. But anyway, we're going to talk next about how to use a random digit table, and we'll do a couple problems using that, and then that'll conclude our section 1.